Yeah, you guys are just the newbies.
Okay, so we got some good stuff today. We're getting into some good physics now. This is good. We've gotten through all the nitty-gritty. Now we're going to look at two-dimensional dynamics. This is good stuff. So we're going to look at an example today. We're going to look at kind of explain something that's an interesting, dangerous occurrence. So we're still in the midst of winter. You know, we're probably through the worst of it, but you never know. We could still get a late winter storm here. So winter storms. Now over here on this side of the state, we get better storms. Ours are more snow, which is good. But you know, having lived on the west side, a lot of times in the winter, if you get a storm, it's freezing rain. That's the worst. Freezing rain is more dangerous. Freezing rain causes problems.
It's scary.
It is. It's scary. It is scary. Yeah. It's not only does it make the roads really slippery, but it's ice is heavy. And what freezing rain is, remember, freezing rain, when precipitation falls through a warm layer and so it turns liquid and then it falls into a cold layer at the ground where everything's cold, it lands as a liquid and then quickly freezes, right? And so that's bad for trees, obviously. How come? So what's it do to trees?
Water in the tree expands and crack the tree.
Well, that's true, but freezing rain, typically that's not the problem. That's when it gets really cold, right? When it gets. But what happens to that? I mean, the ice is heavy. The ice gathers on the limbs of the tree and it snaps the limbs. Yeah. Okay, the other thing that can happen is it can, and this is more dangerous, is it can rupture power lines, right? It can actually snap power lines.
Like in Spokane.
Yeah, and it's
Notice a lot of wind.
yeah, it's wind, and a combination of the two is even worse. But just the weight of the ice it does frequently. If it's a bad ice storm, you can just bet on the fact that it's going to break some power lines. So why is that the case, though? Think about these power lines. Power lines, even if they're not the big high-tension power lines, you know, they're made of metal, right? It's like a metal cable, and it's a soft metal. Usually it's copper. But if it's a metal, you know, the size of your finger, that's a pretty big cable, right? That should be able to support a lot of weight. Well, it turns out that the breaking point for most power lines is when they get about 500 pounds of ice on them. It's not very much. 500 pounds and that's not a big deal. I mean, you could take one of these power lines, and even though it's a copper conductor, I mean, you know, it's soft metal, you could easily pick a car up with that thing, right? It's not, so something's going on here. It's not, you know, it can't just be the weight that's going on. So we gotta analyze this situation. As physicists, we gotta get to the bottom of it.
Wait, is that 500 pounds like between the telephone or the power line poles?
Yeah, between the between the power line poles. So we're gonna do some physics here, and I think this is kind of a good exercise because it teaches and illustrates kind of the new topic we're talking about, but it also illustrates how physicists think about things. And what you'll notice is we're going to try to simplify this problem quite a bit. We're going to simplify the math. We're going to try to boil this down to a relatively simple dynamics problem. If we dealt with it to a higher degree of accuracy, it would be more complicated. But we're not going to do that, and you'll see why. So first of all, here's what power lines typically look like. So regardless of the height of the power lines that are 200 feet apart typically sag about 17 feet at the most. It might be considerably less than that. Okay, but 17 feet is about what you'd expect at the most. Okay, that's kind of a complicated picture because the shape that line makes is called a quaternary, and it's defined by a hyperbolic trig function, which is, you know, we haven't dealt with those in physics. Maybe did you deal with those when you took your physics class, quaternaries and?
I took calculus.
I mean your calculus class. I mean.
No.
No, it'd be probably something you'd generally run into in like your second semester college calculus class. You know, we won't get to it. We could, but we just won't this year in our calculus class. We'll spend time on other stuff. But we can simplify this a little bit. Let's instead, let me exaggerate this just a little bit so I can draw it better. We're going to treat the line as being a flexible, massless line. Okay, anything that's Any flexible medium that transmits a force, we call a line in physics. Which isn't so surprising when we call it a line in everyday life too, I suppose. This is, I'm going to exaggerate this just a little bit. If this is the sag and that's 17 feet, what we're going to do is let's treat it like a triangle instead. Let's treat it like that. Okay, so we're going to assume that the weight is all supported in the middle of that line, which obviously isn't a good approximation. The ice is going to be distributed along the entire line, but it will mostly be in the middle. There's going to be an abundance of ice in the middle, however.
It's sagging, so it's not.
Yeah, so it's sagging, and so the liquid water runs towards the middle as it freezes. Yeah, so you do get more in the middle. 500 pounds, let's just say, to make it a nice round number, let's just say 250 kilograms. That's a little more than 500 pounds, but we'll just go with 250. Let's investigate why this happens. So now, let's look at this from the perspective of the ice. There's the ice in our model, right? 250 kilograms of ice suspended from this line. What are the forces acting on the ice? Okay, so there's gravity, right. So let's draw a free body diagram to represent this, how about? So we've got here's our body, there's the ice. We've got gravity acting in which direction? Straight down. Right. And what are the other forces acting? Tension. Yeah, that is the exact correct word. Tension is the physics word that we use to describe force that is transmitted along a flexible line. That's what tension means. Okay? You can talk about tension in a string or tension in a cable or something like that, right? So we've got these tension vectors. Now, in what direction do the tension vectors act?
Opposite of the force pulling.
Well, okay, but this is, the gravitational force acts down, right? The arrow points in the direction the force is acting on the ice. In what direction do the tension vectors point?
Well, don't they point like equally distant like this way, so then they cancel out and just be up?
So could this be, for example, maybe this could be a tension vector right there?
But then there's
You think?
On a triangle line, would you just travel the direction of the line?
It would.
Yeah.
That's what I'm getting. It has to travel the direction of the line. Now, why does that have to be the case? Well, think about the alternative. This is a flexible line, isn't it? It can move, right? So if the tension vectors were acting in a different direction, what would the line do? Move. It would just adjust itself, right? It's going to move the line if the force is acting in a different direction, right? So by definition, the tension vectors always act along the path of the line, okay? Which is convenient. So then we get these tension vectors acting like that, right? We'll just call that T. Okay, this is a little different than last chapter, though. It's a little more complicated. Last chapter, things always worked out nicely, where our forces were either horizontal or vertical forces, right? 1 for 3 is not terrible. The gravity is vertical, right? The weight of the thing is acting vertically, but the other two are not. The other two are not acting vertically or horizontally, right? So what do? Well, our goal here is we want to be able to do the same kind of stuff we did last chapter. Think what we did last chapter. We didn't, it was easy enough that we oftentimes bypassed some of the steps that we're always going to take now. But at one point or another, we all were involved in a discussion where we talked about this. We said something like this before, right? We said the x component of the net force, meaning the horizontal component of the net force, equals the sum of all of the forces that were horizontal forces last chapter, right? Like in some cases, those were pulling force and friction or something like that, right? And so we added those up, and those were always equal to ma, but specifically, it's going to be the horizontal component of acceleration, right? Well, in this case, what can you tell me about that ice and its motion? Is it moving? It's at rest, right? So what's the acceleration in any direction? 0. Yeah, the x component and the y component of the acceleration in this case would both be 0, right? So we want to come up with some equation where we get some forces or some components of forces add to 0, right? And then the same thing for y, just like we did before. We're going to say that the y component of the net force equals the sum of some vectors, right? Some forces that are acting vertically. And in this case, it's also equal to 0, right? The question is just, though, what are the things that we're adding up, right? Well, in order to get components that we're going to be able to add in horizontal and vertical equations of motion, we have to decide on an orthogonal coordinate system. That's a big, scary word, but can anybody remind me, what does orthogonal mean? Mutually perpendicular. Just means they're at right angles, right? So like the x and y axes are orthogonal, right? They act at right angles. So we've got to decide on some directions here, some right angle directions that fit this picture the best. Suggestions?
Just use MG as well.
So we use, okay, so how about just x and y, right? Instead of having to pick something complicated, why not just pick x and y? It makes sense because gravity acts vertically, so one of our vectors is already acting in the y direction, right?
Yeah,
So we
it's
knocked 1 out of 3 is taken care of.
Because it's a triangle, you're not gonna get any more than.
Right, and we're not gonna,
Not any more than one.
yeah, we could only get 1 at the most, and why not pick the one that's, you know, that's acting vertically? Because vertical and horizontal are pretty natural directions for us to deal with. That's what we almost always deal with in math, right? We have the x and y axes, and we break things up based on those axes. So that's what we'll pick. To do that, though, we've got to take these tension vectors, and we have to break the tension vectors up into components, because they are not acting horizontally or vertically. So we've got to trade them for horizontal components and vertical components that add tip to tail to make the original vector, because we always add vectors tip to tail, right? And all we're doing is we're trading t for the sum of what we might call t sub x and t sub y, right? In other words, the horizontal component of tension plus the vertical component of tension, added tip to tail, equal t, right? And so we could, oh, what did I just do? I didn't want to do, that's for sure. So we can kind of do something like that, maybe, to just remind us that we got rid of the tension in favor of the components. And we get the same thing on the other side, wouldn't we? Over here, we would just get t sub x acting to the left this time instead of the right, and t sub y acting up. Okay, make sense? Okay, so now we started off with our original free body diagram, and what we've produced is something better. We've produced something called an orthogonalized free body diagram, where all the forces are broken up into orthogonal components. So our orthogonalized free body diagram, that sounds really impressive, I know, but it's not that big a deal, would just look like this. Mg points down. Now what are the components acting up going to be? T sub y and t sub y. So 2 times t sub y, right? Which we could, if we want to, just represent like this. Right, we add vectors tip to tail. So we're going to add all the vertical components tip to tail. What about the horizontal components? Okay, so I'm going to get t sub x to the right and t sub x to the left. They will, won't they? Yeah. Yeah. Okay, and there we go. Now the only thing left to do here is we need to be able to write down what t sub x and t sub y are in terms of t, right? How are we going to do that? Say it again.
Don't you have to do like the sine cosine?
Ah, okay, yes, we're going to need an angle, aren't we? Right? We're going to have to use our right triangle trig stuff. Okay, so we got to go back up to this picture, and we need to define an angle. Remember that because the tension vectors act along the lines themselves, right? We can go back to the physical picture to determine what the angles are. Because wouldn't you agree, what I mean by that is, wouldn't you agree that, for example, this angle right there is the same thing as, well, okay, if that's theta, We gotta go back to geometry for a second here. Let's draw another parallel, a line, horizontal line here, right? If that's theta, would you agree that this is theta?
Yep.
Okay. And so that's the same theta, isn't it? Right? Because the tension vector acts along the line. Does that make sense? So what's theta going to be? How are we going to define theta? We know that from this picture, that's 17 feet, and this distance right here is 100 feet, because the whole span is 200, right? So what's theta? How am I going to define theta? What's a relationship that defines theta? A SOHCAHTOA relationship. Tangent would, wouldn't it? So tangent of theta equals opposite, which is 7. Let's use this theta, which is 17, divided by adjacent, which is 100. And I could also add that 17 feet, and that's 100 feet. If I want to use this triangle, maybe that's easier to see. And that's a right triangle, isn't it? Right? Okay. So there's tangent theta. So then what is theta equal to? Theta is just, how would I solve for theta? Arctangent or inverse tangent, right? You ever remember that? So theta, I'm going to write this. So I'm running out of space here. So theta equals inverse tangent or arctangent of 17 over 100, which is that. I just remember that from before. Okay. About 9.65 degrees. Okay. If we do it on our calculator. Okay. So then, now we can find out what T sub x and T sub y are, right? Let's go ahead and before we do that though, let's write down our equations of motion. How about? Okay. So let's go up here and let's fill in these blanks. Just before we mix it up with cosines and sines and all that stuff, let's just write it in terms of horizontal and vertical components of tension. So somebody tell me, what are the forces acting horizontally? Because I want to find the net force acting horizontally, though. Horizontal component. So I get a positive T sub x and a negative T sub x, and they must add to 0 because the acceleration is 0. Okay, well that's not too enlightening, is it? If I subtract something from itself, I better get 0. Okay, maybe we get something better here. What about the vertical component of the net force?
Ty minus mg.
Yeah, good. I'm going to get ty plus ty, which is 2 t sub y minus mg equals 0. Okay, maybe that's better. Okay, so now we want to solve for t, so we need to know what t sub y is, don't we? Right? So what is t sub y? Well, if we go up here and we look at this picture, right? Here's the picture that relates t sub x and t sub y and t.
And you just do m times g.
Couldn't be what?
And you just figure out like t
M
sub y
times
is by doing m times mass times gravity and then dividing that by 2.
Well, sure, but that's only finding out what t sub y is. We want to know what the actual tension in the line is. No, we want to know. See, our goal here is, and I guess we want to think what we're trying to do. We're trying to explain why it is that these power lines break when they get only wimpy 500 pounds of ice on them, right? And to do that, we want to see, well, what is the tension in the line going to be, you know, that supports 500 pounds of ice? And you'll see, it'll make sense here in a little bit. But we need to solve for t. So let's go back up to this picture now. And here's the other thing I really want to review. This is pretty crucial. We went through this stuff, but it's been a while ago. What is the SOHCAHTOA relationship between t sub y and t? And let me maybe move that. Oops, move that t up here like that. What's the SOHCAHTOA relationship? It's a sine, isn't it? So sine theta equals opposite divided by hypotenuse, right? So if I solve that for t sub y, I would just multiply both sides by t. Agreed? So t sub y equals t sine theta. We didn't need it this time, but what would t sub x probably be? T cosine theta, that's right. Okay, so there's a shortcut, remember. You can go through that process every time if you want to. You can always just define a SOHCAHTOA relationship in terms of the component you're trying to find and the hypotenuse, the vector, right? But you always know, now think about this, what's bigger, the vector or its components? The vector is always going to be bigger than any one of the individual components every time, isn't it, right? So if t sub x and t sub y both have to be smaller than t, guaranteed, am I going to multiply or divide by cosine theta or sine theta? I gotta multiply, because think about what sine and cosine theta do. Sine and cosine theta are always going to be less than or equal to 1, right? They're never going to be bigger than 1, so multiplying by sine or cosine theta can only make something smaller, right? Dividing by sine theta or cosine theta would do what? Make it bigger. And so sometimes there's a little bit of confusion about that. People think, oh gosh, I can't remember. If I multiply or divide by sine theta or cosine theta to get a component, you always multiply, because you're getting something smaller, right? The pieces, the smaller pieces of the whole. Which one goes with which? It's easy to tell, because you just look up here and say, well, is it a horizontal, is it an opposite side deal or an adjacent side deal? If it's opposite, it's sine. If it's adjacent, it's cosine by SOHCAHTOA, right? Okay, so then if now we know that t sub y is t sine theta, and theta is just that's 9.65, right? I'll just write theta because that's easier to write. What do we get here then? If we solve this, or if we substitute, we get 2t sine theta minus mg equals 0. So what are the steps in order that I'd have to go through to solve for t? What do I do first? I'm going to add mg to the other side and then divide by 2 times sine theta. Yeah, to get the t by itself, right? So if I do that stuff, don't I just get t equals mg divided by 2 sine theta? Okay, well let's look and see what that turns out to be, because sine theta, or theta is 9.65, right? Okay, so let's calculate this. What are we going to get? So I get, mass we said was 250 kilograms times 9.8 divided by the quantity, 2 times sine of 9.65. And what do you want to make sure your calculator is in before you do this?
Degrees.
Degrees mode this time, because we're actually using degrees, right? That's the biggest mistake people make when they're doing trig stuff on a calculator, is calculator's in the wrong mode. All right, so 250 kilograms, which is about 2,500 newtons, is requiring how much tension? Oops, how much tension? So over 7,300 newtons. So it's almost tripling the amount of tension in there to support that weight, right? And this is actually a pretty generous situation, because 17 feet, that's the maximum. I mean, typically it might be 10 feet, right? What if it was 10 feet? Well, if it was 10 feet, then what's theta going to become? It would have been arc cosine, or arc tangent, sorry. Arc tangent of 10 over 100 would just be 1/100th, which would have been, oh, I can't be right.
Just 0.1.
Oh, 0.1, whoops. That's right. So that would have been about 5.7 degrees. Okay, so what would that have been if we went up and recalculated that with 5.7 degrees, let's say? and it's multiplying the tension by a factor of 5 in that case. So you can see why that would do the trick. That's a lot, right? All of a sudden now, what do we got there? We got like 500 pounds is all of a sudden 2,500 pounds, right? It's like you're suspending a car from that thing instead of just some ice. And so you can see why that would, that would tend to do the trick, right? Okay, make sense? Okay, so why is it happening? Well, look at of that large tension in the line, only a very small piece of that is actually being used to support the weight, right? So you have to generate a lot of tension, a whole lot of extra tension to get enough a large enough vertical component to support the weight of the ice, right? What's happening to most of the tension in the line? What's happening to most of that tension in the line? Is it useful? What's it doing? It just cancels out. It's just pulling against itself horizontally, right? Okay, so this brings us back to did I pose the question about pulling the car out of the ditch to you guys?
Yes.
Not to our part.
To me, no, and you did.
Oh, okay, but I didn't to the class. Okay, so here's an interesting physics solution to a real life problem. So let's say you find yourself, your car is stuck in some kind of a rut. Maybe it's in the snow, maybe it's in the mud, who knows. But you've got to move this thing a little bit to get it back up into where it's got some traction. The wheels can drive. Okay, so what do you got at your disposal? Let's say you've got a long piece of non-stretch tow rope, and there just happens to be a tree trunk that's, let's say, 150, 200 feet away. What do you do? Yeah, that would work, wouldn't it? Right? So if seen from above, if this is your car, I actually did this once in college. I had to do this, and it really does work. Physics came to the rescue. So here's the tree trunk, and here's your line going out to the tree trunk. What do? Well, you obviously can't push hard enough to push the car yourself, but it doesn't take a tremendous amount of transverse force to provide a pretty high tension. And what's the force that's actually going to pull the car out? Tension. Yes, the tension in the line that's going to pull the car out, right? And so, ideally, what you got to do, if you really want if you're with somebody, it makes it a lot easier. What you would do, and I should preface this by saying, it's critically important that it is non-stretch material. You got to be so careful when you're dealing with tension in a flexible line if the line stretches. How come? Because it could snap back. Yeah, probably my best friend, this has been, I don't know, a long time ago, 8, 9 years ago. He was pulling at Priest Lake, he was pulling his shore station out of the lake at the end of the season. And he bolted, you'd think this would be pretty secure. He bolted a ring to a tree, and he hooked up a winch to his shore station to kind of tow it up along the bottom of the lake, to pull it out of the lake. And the bolt worked free, and it was just horrible. The thing, it was probably 100 feet away, 150 feet away, and it snapped back and hit him in the face, and it just fell out. I can't believe it's a miracle he survived, but it broke, orbital bones, and it was because all that energy was stored in that because it stretched. So you don't want to you'd rather use something like chain that's not going to stretch if you ever can, seriously, because then it's not dangerous at all. The chain breaks, it just falls to the ground. But anything that can stretch is you're investing energy in that. We'll talk more about that a little later too. So this is not stretchy material, right? You push a little bit on this and you move the car, and then your partner just pushes something behind the tire so they can't roll back. Then you tighten the line again, and you do it again. Just incrementally, you just kind of ratchet this thing out. And you can get, if you do it that way, you can get amazingly high forces. If we go back to our equation here, and let's just say that we're pushing with, that's quite a lot of force to push with, but you maybe could. Let's say that this angle, instead of being like a 5-degree angle, we really tightened up that line so it's like a 2-degree angle. Look at the amount of force you can generate when you do that. Where am I here? Oh, frozen. Where am I? Yeah. Okay, so let's make this. If that's a 2-degree angle, look at that. It's pretty amazing. Right, you're turning 2,500 newtons of force into 35,000 newtons of force. Right? That's a lot. So that'd be enough, 35,000 newtons, boy, that'd be enough to probably pick off the ground like just about 2 Suburbans. So you could do that. Your own body, measly body could do that if you had a long enough piece of line and it was strong enough and you could push transverse to it. And so it's a relatively easy thing to do. Right? Good to know. You never know. You might need to do this. Does that make sense?
Yeah.
All right. By the end of the year, you're going to be able to MacGyver yourself out of anything.
MacGyver.